Okay, so we're on 651 now. Use table 6.3 to predict the outcome of the following reactions. If no reaction occurs, write NR. If the reaction occurs, write a balanced chemical equation. So we have what we call an activity series table, and we're going to be given different atoms of metal and ions of a different kind of metal. And we're going to determine whether or not the reaction potential of the two atoms, or the atom and the element, are such that they would like to exchange electrons, okay? And again, in the activity series here, we can look at this activity series. This is rated here. We can look at the activity series, and in the activity series, we can see there's a list of metals here and a list of their ions over here, all right? And we remember this activity series by looking at the top one and seeing that gold we know wants to be a metal. It doesn't want to be an ion. That's why when you go digging for gold, you find it as the metal. You don't find it as the ion. Whereas this bottom one down here, or ones down on the bottom, near the bottom, sodium, for example, you never find sodium metal when you go digging. You always find the ion. So sodium prefers to be an ion, or the redox potential is such that in the presence of other things like chlorine or oxygen, it will become an ion, all right? So the ones down here prefer to become an ion. The ones up here prefer to become a metal, okay, in terms of their redox potential. Now, we talk about things preferring, you know, it's like a person or something. It doesn't have any preference. It's just its energetics, its redox potential. It's the potential at which it's going to hold the electrons relative to the other elements that it's in contact with, okay? And this is an activity series, and we call that active, right? Gold is not a very active metal. The ion species, you could consider it as very reactive because it wants to become metallic. Just like cesium or sodium down here are very reactive, they want to become ions, and their ions aren't very reactive. They're relatively stable. Okay? So we can use that activity series like that to predict the kind of reactions that are going to occur, or if the reaction is going to occur, between the given metals and ions. So in the first one, we have iron and magnesium, and iron atom, magnesium ion, right? So we look and we say, okay, so is iron want to become a metal or an ion at the expense of magnesium ion becoming a metal? And we see that magnesium is lower than iron. Therefore, magnesium ion isn't going to want to become a metal at the expense of iron becoming an ion. It would be the other way around. So this is not going to occur. This is no reaction here. All right, chromium and lead, Cr and Pb. We have to find the chromium on here, chromium, and we find the lead. So lead is less reactive. So if we have the lead ion, it is going to want to become the lead metal because the lead metal is less reactive than the chromium atom metal. All right, so we have our second one. What does it say to do? Predict the outcomes of the following reactions. If no reactions occur, write no reactions. If the reaction occurs, write a balanced chemical equation. So we have to write a balanced chemical equation here now, because this reaction is going to occur. So we have a +2 chromium, and the lead is the +2 ion. All right, and the products here are going to be the chromium ion, +3, chromium +3, and lead metal. All right, now if this is going to occur, we have to look at the half reactions, pull them apart, and you'll see that these half reactions are very easy because they don't have any oxygen or hydrogen in them, just electrons, right? So we need 2 electrons on this side, and for the chromium, going to chromate ion, or yeah, chromate ion, chromium, chromide. Lead, no, the chromium ion. That's what it's called, chromium ion. Cr +3, 3 electrons. So we're going to need 2 of these and 3 of these. So we need 2, 3, 2, 3. All right, so that's B. C, silver ion and iron. Ag ion and iron. I already know that this is going to occur because silver metal is much less reactive than iron, right? Silver they made coins out of it. So I know that this is going to go to silver and that this is going to go to Fe. And on the table they give us Fe2, I think. Oh, yes, Fe2. So that's the one that we'll use. All right. So we're going to need 2 silver ions for every Fe ion, right? And again, it looked like it was balanced here in terms of the atoms. If you just look at this, there's 1 atom of iron, 1 atom of iron, 1 atom of silver, 1 atom of silver. But we know that if we draw the half reactions out, that silver ion gives up 1 electron based on this thing here, and we'll do it here. Ag plus an electron goes to silver at metal. Iron metal goes to iron ion, and it yields 2 electrons. So we see that we have to multiply this one by 2 so that the electrons will cancel out. So that's how I knew we needed 2 silver ions and silver atoms. Okay? The last one, silver metal and gold ion. Silver metal and gold ion. Now, gold or silver is very noble, but gold is even nobler or less reactive, the metal itself. So we're going to go from the gold metal to the gold ion to the gold metal, and the silver metal is going to go to the silver ion. And we're going to need 3 of those silver ions because each one gives up 1 electron to give 1 ion of gold to a metallic gold. All right? And again, you can balance that out with the ion electron method that we've been doing before, but we can visualize it because there's no hydrogen or oxygen, so it's easy to see. All right, 653. Guess we can check and look at the back, make sure we didn't miss anything there. 651. Yeah, looks good. Okay. (653). Following reactions occur spontaneously. List the metals, plutonium, platinum, and thallium, in order of increasing of ease of oxidation. All right? In order of increasing ease of oxidation. So the easiest to be oxidized should be on the far right. The hardest to oxidize should be on the left. All right? So we see that plutonium and thallium. Plutonium is more easily oxidized than thallium because plutonium gives up its electrons. So plutonium is easier oxidized than thallium, and that's what they said. Put the easier oxidized ones on the increasing ease of oxidation. So this is increasing from left to right. So plutonium is easier to oxidize than thallium. This is greater in terms of it's more easily oxidized. All right, ruthenium and platinum. Ruthenium and platinum. It looks like ruthenium is easier to oxidize than platinum. All right, and then thallium and ruthenium. Thallium is easier to oxidize than ruthenium. Thallium is easier to oxidize than ruthenium, right? Because thallium is being oxidized by ruthenium. Therefore, we can put this in here, ruthenium, and we can put this in here, platinum. So there should be our answer. Okay? So we can double check that in the back. 653. Platinum, ruthenium, thallium, plutonium. All right. (655). The following reactions occur spontaneously. What reaction will occur if a mixture is prepared containing the following: cadmium nitrate, cadmium nitrate, thallium, and thallium chloride? Please refer to the problem 65.3. The following reaction occurs spontaneously. Ruthenium with cadmium. What reaction will occur if a mixture is prepared containing the following: cadmium and cadmium nitrate, and thallium chloride? Okay, so we have 653. What following reaction will occur if mixtures contain cadmium, cadmium metal? So here we have cadmium, and we have the cadmium ion plus 2 ion. And we have thallium and the thallium plus 1 ion. Right? So we have the thallium and the thallium plus 1 ion. So they want to know what kind of a reaction is going to occur here. What reaction will occur if a mixture containing cadmium, cadmium ion, thallium, and thallium ion if ruthenium is, according to 655, the first part, ruthenium is, or cadmium is more oxidizable, more easily oxidized than ruthenium. Cadmium is more easily oxidized than ruthenium. And ruthenium and thallium, what did we know about ruthenium and thallium? So we knew from problem 653 that thallium is more easily oxidized than ruthenium. So this is greater in reactivity than ruthenium. And we now also know that cadmium is more reactive than ruthenium. So ruthenium less reactive than cadmium. So yeah, I think that this problem is still messed up, so I have to put that into the syllabus as well. It was messed up last series, and I thought that I looked through it and saw that it was okay, but I guess it's not okay, because you can't tell what's going to happen between cadmium and thallium without knowing, with just this information here. Because it tells you how ruthenium is related to thallium, and the equation tells you how ruthenium is related to cadmium. But unless one is more both of these are more reactive than ruthenium, so you don't know which one is how much more reactive they are. So you can't do that one completely. So we could look up the activity series online, though. We could look up the activity series online, and probably would indicate to us that it looks like cadmium or thallium, no, cadmium is more reactive than thallium. This is what the book says in the back. We'd have to look that up in some other activity series online. All right, 657. Write the equation for the following depiction of the following visualization. So we have 5 magnesium there. Magnesium metal. And we have zinc chloride, 1, 2, 3, 4, 5 zinc chloride. So it looks like we have zinc metal, and there's 10 chlorides in there, it looks like, and there's 5 zinc ions, so it looks like it has a zinc plus 2 charge, because it looks like there was twice as many chlorides to zinc, so that's what the initial compound was. So it's zinc plus 2, which makes sense. That's zinc plus 2. And zinc is becoming metallic at the expense of magnesium giving up its electrons. Okay, so that looks like is what is happening, and that's it. Write the balanced equation for the reaction depicted in the following. 657. Okay, so they wanted, actually, I mean, they wanted, this is correct, but what they did was they just said that there's 5 of these, and they also included the chloride ions, which there's 10 of them, and so there's going to be 10 chlorides at the end as well, and there's going to be 5 of these and 5 of these. So that's fine. 659. 659, write the chemical equation for the following reaction. Uh, 10 lithiums mixing with water to form lithium ion and hydroxide ion and hydrogen gas. All right, so we have 10 lithiums coming together with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 waters. The product is lithium hydroxide. So we're going to have 10. I didn't count them, but we have to have 10, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And hydrogen gas. And this is what happens when you put lithium, sodium, any alkali metal into water. And that's why they call them alkali metal, because you end up with hydroxide ions. So it makes the solution basic. And alkali means basic. All right. Oh, how many hydrogen gas? 1, 2, 3, 4, 5. Okay. Kind of stretching here to make us have more problems. I don't know exactly what we're trying to learn that's new here. All right. And this time they took the lithium and the hydroxide and they separated them, which is fine. That makes sense. That's fine. Okay, because this is a soluble compound, lithium hydroxide, right? Lithium is a group 1A metal. 661. Reactions of oxygen. Write balanced chemical equations for the complete combustion in the presence of excess oxygen for benzene, butane, and paraffin waxed. C21H44. Benzene. C6H6 plus oxygen yields carbon dioxide and water. Now, you can do the ion electron method, but when you do have combustions like this, it works out that you don't have to use the ion electron method. You can just balance them by inspection. So I'll do this one by the ion electron method, and then I'll do the next ones just balancing by inspection. Okay? So the ion electron method, we have C6H6 going to carbon dioxide. We need 2 H2Os on the left here to give us 2 oxygens there. We need to get, we have 4 hydrogens here, 6 hydrogens here, so we need 10 H pluses here. Let's see, is that right? 4 plus 6, 10, double check, oxygen 2, 2. Oh, no, start over. Made a mistake. We did not first balance the carbons, right? We have to balance the carbons first. So let's try it again. 6 there. Now the carbons are balanced. Now we need 12 water molecules over here. And now we need 24 plus 6, 30 H pluses over here. And that's going to require 30 electrons over there. All right, the other one, we have oxygen gas going to water. We need 2 waters on the right because we have 2 oxygens here. And then we need 4 H pluses here. And we need 4 electrons there. All right, so 4 electrons here. 30 electrons here. Did we do this right? Make sure we did this right. 6, 6, 24, plus 6. 6 times 2, 12 times 2 is 24. 5, 6, 7, 8, 9, 30. 30. Okay, so if we multiply this by 30 and this by 4, 4 times 12 is 48 waters. And we see, okay, yeah, 48 waters. What else do we got? Plus 4 benzene, C6H6, plus 3 times 4 is 120 electrons. And we'll leave those out because we see that 30 times 4 is going to give us 120 electrons as well. 3 times 4 is 120 protons, but we'll leave those out because we see we're going to have 120 protons on the other side as well. And then 30 oxygen gases here, right? Okay, so on the right side of the equation, 6 times 4, 24 carbon dioxides. And we don't have to worry about these. We saw that they were going to drop out. And 3 times 2, 60 waters. All right, so we have 48 waters over here. So that's going to leave us with 12 waters over here. And we can cancel out these waters. All right, so we have 4 hexanes, 30 oxygen gases, 24 carbon dioxide, and 12 waters. We can reduce this down, right? So there was probably some smaller common multiple between 30 and 4, right? So anyways, we can divide everything by 2 here. So we have 2C6H6 plus 15 oxygen gases going to 12 carbon dioxide and 6 waters. Okay, so that's probably, hopefully, the answer in the back, 661. 2, 15, 12, and 6. All right, now let's just go back. Oops, lost my eraser. Now let's just go back and do that one by inspection. So if we look at this, we see we need 6 carbons here, right? Oxygen we'll do last. Hydrogen, we have 6 on the left. We're going to need 3 there. And then oxygen, we see we need 12. 6 times 2 is 12. 13, 14, 15. So that's going to be 7.5, half of 15, right? So we multiply everything by 2, 2, 15, 12, and 6. All right, so balancing by inspection is a little bit faster there, but we see, just to double check, 2, 15, 12, and 6. We get the same answer. And that's easy enough. So we'll balance the next ones by inspection. 61, where is that? There it is. Butane, C4H10, or does it say to do it by the... No, it just says to balance the equation. So it doesn't say by the ion electron method, so we're okay. Carbon dioxide and water. 4 here. 5 here, right? Oxygen's on the right. 8 plus 5, 8, 13. Is that right? 8, 9, 10, 11, 12, 13. So we have 13 on the right. So this is going to be half of 13, which is 6.5. Multiply that by 2, that's going to be 13. So that's going to be 2, that's going to be 8, and that's going to be 10. So 2 butanes, 13 oxygen gases, 8 carbon dioxides, 661, 2, 13, 8, and 10. All right. And the last one. C21H44. C21H44. All right. So combine that with hydrogen gas, and then we're going to get oxygen gas. Combine that with oxygen gas, we're going to get carbon dioxide and water. We need to have 21 carbons here. We need to have 22 waters to get 44 hydrogens, right? All right, how many oxygens do we need? 21 times 2, that's 42 here, and 22 here. So we need 64. Oxygen, half of 64 is 32. So that should be it. 1, 32, 21, 22. All right, good. 663. Write the balancing equation for the combination of hydrocarbons in problem 661 in a slightly limited supply of oxygen and a very limited supply of oxygen. 663. All right, so same thing. We're looking at hexane, but now we have to remind ourselves what the limited and very limited supply, right, or scant. Limited and scant amount of oxygen. Where are those reactions? So on 243, we have them summarized for us. Okay, reactions to those. All right, so on 236 there as well. Limited oxygen supply, very limited oxygen supply, are also called scant. All right, so the only difference is the products. Limited, you get carbon monoxide, and scant, you get carbon. Okay, so if we take hexane again, C6H6, C6H6 with oxygen gas. This is limited, and this is scant, which means very limited. All right, so in limited, we get carbon monoxide. In scant, we get carbon. All right, and that makes sense. Not enough oxygen. Some of the carbons get away without the second oxygen, which is normally carbon dioxide. That's the best case scenario. Even less oxygen, some of the carbon gets away with just carbon. Okay? All right, so we balance this equation the same way. 6 carbons here. Hydrogens, 3 there. Oxygens, 6, 7, 8, 9. 4.5, so 2, 9, 12, and 6. So that's 663, 2, 9, 12, and 6. For the limited, for the scant, 6 there, 3 there. We have 3 on the right here, 1.5, so there's going to be 2, 3, 6, and 3. 2, 3, 6, and 3. 663, the 2, 3, where is it? Where did you go? Hello? Hello? All right, so we have 2. Oh, 2, 3, this needs to be multiplied by 2. 12 and 6. 2, 3, 12, and 6. There's the problem. 2. All right, so this is problem 663 with scant and with low or limited oxygen for the first one, and 663. Where are we at here? 663 with limited and scant or very limited, right? And then limited, carbon monoxide is the product, scant, carbon is the product. Okay. So we will just do those ones again. 663 for butane, right? So all we have to do is change this here. C4H10, C4H10, limited, scant, or very limited. All right, 4 carbon monoxide, 4 carbon here, right? 5 here, this is 10 here, so we need 5 waters to get 10 protons. Oxygen, we need 4 plus 5 is 9, 4.5, so we multiply this by 2, 2, 9, 8, 10. This one here we need just 5, so this is going to be 2.5, multiply it by 2, 2, 5, 8, and 10. Okay, so it's 2, 9, 8, 10, 2, 5, 8, 10. And that should be for 663. 663. Oh, wait. 663, the second one. 2, 9, 8, 10, and 2, 5, 8, 10. All right, got it. All right, the last one, paraffin, C21H44, 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 21 here, 21 here, 44, so 22 here, 22 here. This one we need how many oxygens? 21 plus 22 is 43. 43 divided by 2. What's 43 divided by 2? $21.5, so that times 2 is going to be 43. So there's 43, 21 times 2 is 42, and then 22 times 2 is 44. So there's going to be 2, 43, 42, 44. And this one here, we need 22 of those, so it's going to be 11. So 1, 11, 21, 22. 663, right? 663, because we have 2, 43, 42, 44. 1, 11, 21, 22. We got it. We're done. 663.